So for this pi day, I ended up finding a really cool way to calculate pi with an idea called buckling. So for buckling, if you have something long and slender like this paperclip that I just unfurled, and you were to push on it, there's some force at which when you push in, starts to flex outwards. And so we have an equation for this. You can see pi already shows up there. We need E, which is the Young's modulus. This can be calculated with a deformation of the length. I could do that, but I don't have the material. If you were able to pull it and see how much it deforms with some force, you can calculate that. Instead, I'm just going to use the value of 200 gigapascals. We also need I, which is the smallest area moment of inertia, which involves the cross section. Now, for a cylinder, which is what a paperclip is, we can just find the radius, and it's going to be pi over 2 r to the fourth. And so if we just take it, we can see it's about 1.2, 1.02, 1.03 millimeters. So we can keep that for later. We also need K. K is just a constant used for different types of endpoints that we're using. That'll just be 1 in the end, so we'll deal with that later. And L, I'll deal with L in a second. I went and straightened out the paperclip as much as I could. And so the last thing that we need is the force. So I just have a kitchen scale here, which we can turn on. And the plan is I'm just going to push down on the paperclip and see at what force, at what weight this buckles. So in order to keep it steady, I have a clamp, which is just going to keep it held upright. And in order to push down, I'm just going to take another clamp and push down in it. So for that, I'm going to tear it, just so that everything's set up. And then I can clamp this. And I can then push down. Now before I do that, I'm just going to take the length measurement because it's in between these. And you can see the length here is about 130.9 millimeters. So about 131. So we can take that and we can push down on this, and we should be able to see at what point it begins to bend if I do this correctly and it's straight down. Here we go. So that was about 1.3 that I saw, which is about the same that I've seen every time that I've done it. So now we have everything. Let's write the equation one last time. F equals pi squared EI over KL squared. This F we saw was about 1.31 kilograms. We need to multiply that by G to turn into newtons, 9.81. This E I had to look up. It's just 200 gigapascals, which is 2 times 10 to the 11. This I, we know, is pi over 2 r to the fourth. This r, we remember we solved for the diameter. Diameter is 1.03 millimeters, or 0.00103 meters, just to turn everything into SI. So we can just divide that by 2 in order to get the radius. This K, I settled on just using 1. This K depends on the endpoints of the column that we're using, and I can't really say that it was fixed. They were still free to rotate, so that's why I'm going to end up using 1 for this. And it's nice because then that K just kind of goes away. And then we have L. This L we said was 130.9 millimeters, which is equal to 0.1309 meters. So now we have everything. We can solve for pi now. So I'm just going to rewrite this equation in order to set pi to its own spot. So we can say F equals pi to the third ER to the fourth over 2L squared, and that means pi cubed is equal to 2F L squared over ER to the fourth. I've moved all the values now over to Desmos so that we can just type in the final equation that we have, 2F L squared divided by ER to the fourth. We get 31, but we know it's the cubed of it, so we have to take the cube root of this, or just 1/3, and we get a value of 3.15 for pi, which I was not expecting to be as good as that is.